Okay, I guess today is the final class, and we have done a lot of stuff about LP and some stuff from before. Does anyone have any question from what we have done so far? I have shared the notes. So for today, you are not asking any questions, so I'll move on, but I mean, you can ask questions at any time. Okay. For today, I'll do some elementary stuff because we have finished nearly finished this chapter. A little bit is left, and that I'll do, but that won't take long. And we'll do maybe we'll do some fun stuff, and some of the exercises of this chapter. Very nice exercises. So let's start with something not very difficult at all. So we have seen convex functions in the very first class. Lots of examples of convex functions and Jensen's inequality, right? Now, so one of the things mathematicians do is that when they deduce a result like Jensen's inequality from convex functions, for example, so if phi is convex, then phi satisfies something. Phi of integral f is less than equal to integral f composed integral phi composed with f. For anything that you can integrate, for any function f that you can integrate, that is. So when mathematicians prove such a thing, they always ask, it's considered a natural question in mathematics, whether the converse is true. Sometimes it's true, sometimes it's not true. So when we prove A implies B, often it's natural to ask whether B implies A as well. Then you have a characterization of A. So in different circumstances, if you are told to prove A, for example, and instead you prove B, then you have proved A. So that's an advantage. And in this spirit, so isn't that nice? You want to show that the function phi is convex, you need to verify Jensen type inequality for every bounded measurable function for f. Now you might very well say that this is from frying pan to fire, because you are only asked to prove convexity of phi, but then now you have to check something for every bounded measurable function f. Yeah, sure. I mean, it might be so, but nevertheless, in some situations, this might be helpful. That happens. It might look like a much more difficult thing to verify. Nevertheless, there are situations when that can be done. Okay. So to show that this is one of the problems in Rudin towards the very end. So I'll verify the convexity from definition. The definition of convex functions is that if you have 2 points, let's say T and S, you have the graph of the function. You consider the line joining phi T and phi S. That's a line, and the graph of the function should remain below that. This means phi of lambda T plus 1 minus lambda S less than equal to lambda phi T plus 1 minus lambda phi S for every lambda between 0 and 1, and for every t and s on wherever phi is defined. I chose this problem because it involves a nice trick. So this is our point of interest, right? I need to show phi at this point is less than or equal to lambda phi t plus 1 minus lambda phi s. Now the trick is I write this as t and then 0 to lambda dx. That's just lambda plus maybe s, and then 1 to lambda dx. No, lambda to 1. That's the same as all of you have seen such things. In measure theory, we write like that. Integral 0 to lambda is nothing but the indicator function of 0 to lambda integrated over the whole interval 0 to 1. Okay, so that's the same as now that both the integrals are over 0 to 1, instead of one integral being from 0 to lambda, the other integral being from lambda to 1, it's plus, I guess, s indicator so you see I've written lambda t plus 1 minus lambda s, just a number in such a complicated fashion. Give this function a name. Oops. It is a bounded measurable function. Measurable because indicator functions are measurable, linear combinations of measurable functions are measurable, and of course bounded. I mean, indicator functions never go above 1, and you have multiplied by t multiplied by s, so it will at most go up to t or s, whichever higher. And t and s are fixed numbers. So this is a bounded measurable function. All right. So since this is a bounded measurable function, now we invoke what we know. So we know this. Where I put the red tick, we know that for every bounded measurable function. So I use it for this bounded measurable function. Well, integral fx dx we have seen is lambda t plus 1 minus lambda s. That's what this calculation, which is now on the screen, shows. Lambda t plus 1 minus lambda s is just integral f. So this is phi of lambda t plus 1 minus lambda s less than equal to, let's see, what is phi f? What is phi of f at x? Now, that's a difficult question, right? Okay. So where is x? X is between 0 and 1. If x is between 0 and 1, then x is either in 0 lambda or in lambda 1. maybe one of those intervals you have to take an open interval so that the intersection is not there. Maybe take close 0 and open lambda. If it is there in 0 lambda, then the value of the function fx is just t. So then phi of f of x is phi t. Agreed? So when okay, let me, I don't know how to write, just give me a second. So when I write, so I can write 0 to lambda, it becomes phi t dx. There is no dependence on x. In the lambda to 1 portion, I've just written the integral 0 to 1 as 0 to lambda and lambda to 1. And maybe the intervals having intersection after all doesn't matter because my measure is such that on the singleton lambda it's 0. So perhaps it doesn't matter. But if it matters, do make the necessary correction. And here on the other place, if x is in lambda 1, then value of phi fx is just s. Sorry, phi s. Value of fx is s. So isn't that lambda phi t 1 minus lambda phi s? So phi is convex. So that's any question on this? Okay, once again, quickly, phi is a real function which satisfies phi 0 to 1 fx dx less than equal to integral 0 to 1 phi f x dx. For every bounded measurable function f, then phi is convex. So that means I choose 2 points, t and s. I have to show that phi of lambda t plus 1 minus lambda s is less than equal to lambda phi t plus 1 minus lambda phi s. I do this very smart trick of writing lambda t plus 1 minus lambda s as integral of certain f, that f is this. Where is that f? Yeah, that f is this. Now, the moment it's integral of certain f, so phi of lambda t plus 1 minus lambda f is phi of that integral, which is given to be less than equal to integral phi f. Phi f turns out to be lambda phi t, integral of phi f turns out to be lambda phi t plus 1 minus lambda phi s. Okay. These are kind of standard measure theoretic tricks. The other problem I have chosen, this again, an exercise from Rudin. Maybe this is the last one or the last but one or something like that. Because this is interesting. It does link with other things which perhaps I cannot explain, but this has an appeal. Suppose you have a finite measure space. Finite measures are very nice. If you scale the whole space, then it becomes a probability measure. And they're not trivial. Lots of things are highly non-trivial. Not just because the measure is finite, things don't become easy. They do become easy to some extent, but not quite altogether. So f is a non-zero function in L infinity. Define alpha n equal to integral, sorry. Can anyone tell me why alpha n should not be infinity? Okay, complete silence. This is interesting.
Sir, mu is, this is finite measure space.
Yes, because it's a finite measure. So you can take norm f to the power n outside and you will still get a, so here finite measure is being used. Then the interesting thing is alpha n plus 1 by alpha n, this limit is norm f. Note that this is non-trivial because there is no way of guessing it right from the beginning that why should this why should this happen? So this is a surprise. Okay, first of all, note that if alpha n0 equal to 0 for some n0, then f is identical, sorry, not identically 0, almost everywhere. Because mod f to the power n is a non-negative function and mu is a positive measure. All these measures are positive measures only. So it's a positive measure, and if that's a non-negative function, integration is 0, that function has to be 0 almost everywhere. So that's not allowed, right? Because we are given it to be a norm f infinity is positive. So alpha n's are positive for all n. That's number one. Also, one thing is pretty clear. Since mod fx less than equal to the norm f almost everywhere, that's the definition of the L infinity norm, as we saw last time. We have alpha n plus 1 equal to integral mod f to the power n d mu. I've written n plus 1 as that. I take out one of them, and then it becomes integral mod f to the power n d mu, and that is norm f times mu n. So for n plus 1 by alpha n less than equal to this. So you already know that the limit is less than equal to this. You only have to show that the limit cannot fall below. Now that obviously the hint is, if you want to show that the limit is actually equal, then you will have to put the limit above the norm f, above norm f minus epsilon for every epsilon. So start with an epsilon. For any epsilon positive and obviously less than norm f. The set f which depends on epsilon, maybe I write f suffix epsilon now and might drop the epsilon subsequently if it becomes too cumbersome. As positive measure by definition. Agreed? So, if it had 0 measure, then norm f would not be norm f. It would be norm f minus epsilon. Okay. I look at alpha n, which is integral mod f to the power n d mu. Now I do a little trick here. I'm trying to apply Holder's inequality. Remember Holder's inequality, integral f g d mu, and then which is integral f to the power p d mu whole to the power 1 by p, and integral g to the power q d mu whole to the power 1 by q, where p and q are conjugate exponents, that is 1 by p plus 1 by q is equal to 1. Now here, I don't have two functions, I have only one function. So I'll apply it to this function, mod f to the power n, and the other function is 1. And no, wait. Be careful here. Yes. So that's number one. The function is mod f to the power n. The other function is 1. And what are my p and q? As they are as I'm writing. My p is n plus 1 by n. So 1 by p is n by n plus 1. That means 1 by q will have to be 1 by n plus 1. So q is n plus 1. Okay. Again, a trick, but again, these things appear all the time. Is that clear to everyone? I'm applying Holder's inequality with the first function mod f to the power n, the second function constant 1. So I have mod f to the power and p equal to n plus 1 by n and q equal to n plus 1. That's all. Well, of course, this is equal to integral over x mod f to the power n plus 1 d mu. Oh, there is a d mu here. To the power n by n plus 1 integral d mu so that's the same as, so that is alpha n plus 1, right? The thing inside the bracket. But then I have a power and then I have mu x to the power 1 by plus 1. So I have a relation alpha n less than equal to something or other. So 1 by alpha n, which is our interest, because finally we have the ratio alpha n plus 1 by alpha n. So 1 by alpha n is greater than equal to alpha n plus 1 to the power n plus 1 by n. Oops, sorry. Minus n by n plus 1 mu x to the power minus 1 by n plus 1. So alpha n plus 1 by alpha n greater than equal to, so here I'll have alpha n plus 1 to the power 1 minus n by n plus 1. So n plus 1 minus n by n plus 1, that's 1 by n plus 1. And this mu x to the power minus 1 by n plus 1. Okay. Now alpha n plus 1, okay, let me write again or once more what alpha n plus 1 is. Okay, just in case this is getting too cumbersome, see what I did is as follows. I haven't used, maybe I shouldn't have introduced f epsilon that early. I could have introduced it later. What I've done is I have applied Holder's inequality to alpha n, and thereby I have deduced that 1 by alpha n is greater than equal to alpha n plus 1 to the power minus n by n plus 1 mu x to the power minus 1 by n plus 1. This gives me the advantage that alpha n plus 1 by alpha n is greater than equal to alpha n plus 1 to the power something and mu x to the power minus something. I am desperate to bring in norm f infinity. Okay, norm f infinity minus epsilon, in fact. How do I do that? Okay. So this is what it is, mod f to the power n plus 1 d mu integration 1 to the power 1 by n plus 1. Now, that's greater than equal to integral over that f because you are after all integrating a non-negative function, and if you integrate over only a part of the set than the full set, then obviously the integration over the part of the set will be smaller. Now here on f epsilon, so at this is I should have introduced f epsilon only at this stage. F epsilon is that set on which mod fx is bigger than norm f infinity minus epsilon. So consequently here, this mod f is bigger than that, so greater than equal to norm f minus epsilon, and the whole thing of course now comes out, and then you have mu f epsilon to the power 1 by n plus 1 mu x to the power minus 1 by n plus 1. But now I think I'll have this n plus 1 over the whole thing. Yes. So that is norm f minus epsilon times mu f epsilon by mu x by n plus 1. Mu f epsilon is positive, so this quotient is not 0. Okay. So finally, this is the calculation I did. Alpha n plus 1 by alpha n is greater than equal to norm f minus epsilon times that. Okay. Let n go to infinity now. So limit. So as n goes to infinity, this thing, the last quotient to the power 1 by n plus 1, as n goes to infinity, 1 by n plus 1 goes to 0. So the whole thing goes to 1. Since epsilon is arbitrary, we are done. I mean, if one is very pedantic, well, one will ask about limit, lim sup, etc. That is, how do I know that the limit exists? But these two things do imply that the limit exists. Which two things? First thing is, yes, this, that alpha n plus 1 by alpha n is always below norm f. Of course, that doesn't stop it from oscillating. So that's one thing. The other thing is, this inequality. Alpha n plus 1 by alpha n is norm f minus epsilon times something that surely goes to 1. And these two things imply that limit is equal to lim sup. Okay. I'm not going to that proof. The limit is bigger than equal to norm f minus epsilon for every epsilon, and epsilon positive is arbitrary. So we are done. Okay, I wanted to do these things, but other than this, there is only one little bit left from the chapter. Maybe I'll do that, and then we finish. We'll finish early today, but everything has been done. In fact, more has been done. Yeah.
Can I make a comment here?
Sorry?
Sir, can I make a comment here? You have actually also proved that if you take the p norm of f, that will go to norm f infinity.
Something like
because
that, yes.
No, actually, whenever this limit of ratio exists, then the limit of alpha power 1 by n also exists, and that equal to norm of f infinity.
Oh,
This was
okay.
done in the first tutorial actually.
This was done in what?
First tutorial.
Oh, okay. Whenever the limit
AFS.
exists, then alpha n to the power 1 by n limit also exists.
Yeah, and that is also the same limit.
Valuable comment, Susan. Thank you. Yes. So the P norm goes to F infinity, the infinity norm. Okay, good. Okay, I think right. We have done much more than actually is there in chapter 3. So this little bit that is left is about C0x. So locally compact x. Okay. So what's C0x? What is Cx when x is compact? When x is compact, x is all continuous functions. So here also you can take all continuous functions. Nobody is stopping you. However, you won't be able to give it a norm because locally compact x, so continuous functions might become unbounded, like on the real line. I mean, you have umpteen number of unbounded continuous functions. A straight line going from minus infinity all the way to plus infinity. So you won't be able to take sup norm. C0x consists of those functions f for which the following is true. Given any epsilon positive, there exists a compact set K, compact subset of X, such that mod fx is less than epsilon for x in K complement. So on a compact set K, you allow the function to be anything. You know very well that a continuous function cannot be too big on a compact set. The supremum will have to be finite. And outside a compact set, it's small. So given any epsilon, there is a compact set K, such that outside K, it's small. Okay. Think of something like normal density on the real line, for example. That's a typical example of such a thing. Of course, it's very smooth. You are only asking for continuous functions, so you don't need very smooth. You can have corners. Another way to think of it is why this definition. If you ask this, it's like this. So when you start with a locally compact x, its one point compactification means that you're adjoining just one point to make it compact. This is possible. So if that point is called infinity, then any neighborhood of infinity really is just a complement of a compact set. So what you are saying is the function is going to 0 near infinity. That is, given any epsilon, there is a neighborhood of infinity where the function is smaller than epsilon. That precisely means that the function is going to 0 as in at infinity. That's why. Okay, theorem is, and I'll probably hand wave a little bit here because this kind of argument we have seen so many times by now. C0x is the completion of CCX, functions with compact support. So it involves showing two things. Number one, C0x is complete, and number two, CCX is dense. That's what it means to say that C0x is the completion. Okay. First of all, note that given f in C0x and epsilon positive, get compact K such that mod fx is and as I told you last time, or maybe the time before that, local compactness makes its presence known by Udison's lemma all the time. Get G in CCX, continuous function with compact support, such that 0 less than equal to G less than equal to 1. Gx is 1 for all x in K, and then it decays to 0 outside some open set containing K. Let H equal to Fg, that's a way of smoothing the function, okay? Getting a compact, sorry, not smoothing the function, that's not the right term here. That's the way of making the function compact support. Obviously, where G is 0, it will also have to be 0 because H is F times G. So H is of compact support and it's continuous because it's a product of continuous functions. So then H belongs to CCX, and if you look at norm H, F minus H, what is it? It's the subnorm. C0x. Oh, by the way, why do we make this? Why do we consider these functions which are zero, which are small outside a compact set? So that precisely we can give them the subnorm. For C0x, the norm is the same as Cx when x is compact. That is, namely, supremum over all x in x mod fx. Now that is finite because, say, for 1, I shall find a compact set so that outside the compact set mod fx is less than 1. On the compact set, it's bounded by some m. So maximum of m or 1 will be the will certainly dominate the supremum. Okay, so they are finite, and it's a vector space. So with the supremum norm, it becomes a normed vector space without any problem whatsoever. It's exactly the same as Cx. The supremum norm of this is this minus Fg equal to norm F times norm 1 minus G. Now, 1 minus G vanishes on K. So this thing will only survive, 1 minus G will only survive outside K where F is small. So choosing okay, given okay, maybe so this is less than equal to epsilon times well, if you want to be very crude, it doesn't really matter, 1 plus norm G, for example, and that's it. No, you don't need to be that bad. No, sorry, it's just less than epsilon, because 1 minus G is a function between 0 and 1. Its supremum norm is less than 1, and that 1 plus norm G would actually would run into trouble, because if you look at the argument, it would run into trouble. So it's just less than epsilon, because norm 1 minus G is less than equal to 1. So that's why. All right. So that's the denseness argument. The second thing that you need to prove is that C0x is complete. So let Fn be a Cauchy sequence in C0x. It's a Cauchy sequence in C0x. That means supremum. So the supremum goes to 0. Supremum goes to 0 as nm become bigger, n and m go to infinity. So So mod fnx minus fmx goes to 0 for every x. This is the supremum. So there is a limit function, pointwise limit function. Fn goes to some f pointwise. Exercise, show that f is continuous. First of all, show that. Why is that so? The proof is exactly the same as how you show that a Cauchy sequence in Cx for x compact. First you take its pointwise limit and then you show that f is continuous. Well, essentially because it's a uniform convergence. That's why. So show that f is continuous. The second thing you'll have to show is that f belongs to C0x. But then, given epsilon positive, choose n large enough so that f and fn goes to f uniformly. This is exactly like the proof of Cx being complete. Now, choose a compact set for Fn. Outside K. Now, norm Fn minus f is less than epsilon, which means, so if x is outside K, mod fx less than equal to mod fx minus fnx plus mod fnx. Now, this is less than epsilon, that's less than epsilon, so it's less than 2 epsilon. So, if you started with epsilon by 2, then we'll get, epsilon. The only hand waving I did is to show that the limit function is continuous and Fn goes to f uniformly. But as I said, this is exactly the same as the proof in Cx when x is compact. I think 15 minutes left, but I'll stop with that. There is nothing further. The reason is there is nothing else in the chapter anyway. I have already done more than what is there in the chapter, and perhaps too much should not be done. Then it loses its impact. Then it is difficult for you as well to grasp everything that's been. And we have done some very non-trivial stuff, like the Egorov's theorem and Luzin's theorem. And in the tutorials, certain exercises from this chapter of Rudin are being done. So consequently, a good amount of material has been covered, more than the expectation, I think. So in that case, let's stop here. Any questions?